Hello, in this video, we're going to be looking at multiple representations of functions. So just as a quick refresher, we often see patterns and situations that show a relationship between two variables. These are what we call function relationships. That's the first thing that's going to be really, really important that we understand is that these functions are really relating two variables that possibly impact each other. We can take one of these functional relationships and we can use tables, pictures, verbal descriptions, or graphs to represent that situation. And so that's what we're going to be taking a look at in these examples. The variable that we're going to start with, we're going to call the independent variable. Independent meaning it stands alone, meaning that it's kind of in control of everything else. Everything else depends on the independent variable. So again, the independent variable is staying alone. And you're trying to see if the independent variable causes some kind of change in the other variable. So you're going to start normally with the independent variable. And then based on that independent variable, the dependent variable depends on the independent variable. And so we're trying to find out what makes the dependent variable change the way it does. And usually the independent variable is in control of that. So let's take a look at a situation here. Mr. Goldwasser and Mr. Saxon are planning the homecoming dance and need to order the correct number of tables. The tables are hexagon shaped and 6 chairs will be placed around each table. You see a visual diagram, the picture diagram right down below it with the red dots indicating the number of chairs around each table. So you see that there are 6 chairs around each table. If we took that and tried to organize a table around it, we would look at this and we would see the two variables that we're trying to connect are the number of tables and the number of students. The number of students depends on the number of tables that we have. So if we have 0 tables, we're going to have 0 students that are able to sit there. If we have 1 table, there was 6 students. If we had 2 tables, there would be 12. If there's 3 tables, another 6, so that would be 18 total. And if we had 4 tables, we would have another 6, which would be 24. Now, dissecting the process that we went through here, we really took the number of tables, so like 1 table, and we multiplied it by the number of students. 2 tables, 6 students at each, got us the 12, and so forth. So really what we're doing is we're taking the number of tables and multiplying it by 6 each time to get the number of students that can sit at these tables. Also see is that the number of tables is usually what we call the input. Also like the independent variable. And then, so we took the number of tables and we multiplied it by 6, and that would give us our output. So you'll see that input output will be something that we'll talk about a lot, and the output is usually the dependent variable, and that's also y. So the independent variable is the input, and that's x. So you'd want to organize those in a way that you're going to remember those. And I've organized those to the right here. So describing the mathematical pattern in words, what happened? Really, every time a table is added, we add 6 chairs. That's how I would describe what's happening here. Now, if I was going to represent this on a graph right down here below, I'm going to take my independent variable. My independent variable is always going to be on the x. Remember, it's associated with the x, and the dependent variable is associated with the y. So I'm just going to label those appropriately. Now that I've labeled those with my independent and dependent, notice that also could be referenced in the table. Then I'm going to put increments that will help me fit all of this data on the graph. So these are the increments that I chose. On the x-axis, I chose to go by 1 for the number of tables. And then on the y-axis, I chose to go by 3. So each of these is 3, and I labeled every other 1. So I just spread those out a little bit so we could see and fit everything on the graph. Now I'm just going to take the points from my table and I'm going to graph those. So we had 0, 0 graphed. We had 1, 6, which would be right here. We had 2 and we had 12. That would be right here. Notice every point, there's an exact coordinate for that. And then 318 was right here. And then 424 was right here. Now, if I kept this trend going, if I had 5, I would have 30. So I would keep going up here and I could keep extending this. Now, one of the things I do want to point out here is that these points are the only values that exist for this. So number of tables has to be a whole number. We can't have 2.5 tables. We could estimate that, but really these are just the points, and we could actually use this information to predict in the future as well. So I drew this dotted line in here because we could use it to predict ones in between, but truly we have to have whole numbers in terms of numbers of tables. The other thing that I would point out is that the y-intercept, which actually happens to be the x-intercept as well, the y-intercept, where it crosses the y-axis, is at 0, 0, and that's really important to note. Now we're going to move on to the algebraic rule. We took the input, the number of tables, right up here if we look at our process, and we multiplied it by 6 to get the output. That would be putting it in words. Now, if we're talking about input, we're talking about x, so we're really talking about x times 6, and that's going to get us our y. We could also reverse this and make it 6x, because it's multiplication, and not put the little dot there. It's usually how we'll see it. 6x equals y. So we could actually relate these two variables in this algebraic rule, or eventually to an equation like this, where we'd say 6 times the x value was the number of tables, will be equal to our number of students, which was our y value. Now looking at part B, we're going to answer some questions based on the previous representation. So the first one is, what's the y-intercept? If we look at the graphical representation of this, the y-intercept is the point where it crosses, the function intersects the y-axis. That can be anywhere along here, but what you'll notice is that every y-intercept has an x value of 0. So it's 0, comma, and then some value that's going to tell us how much we move up and down on that y-axis. So in this case, it is 0, 0. That's where it intersects, the function intersects the y-axis. And since the x value right here is 0, x was the number of tables, so we'd say 0 tables would give us 0 students, which basically indicates if we don't set up any tables, no students are going to be able to sit down. The second question is, according to the rule, how many people can be seated at 22 tables? 22 tables. Tables was the x value, so we're going to substitute 22 in for x. So remember, it's y equals, so the number of students is equal to 6 times the number of tables. So 22 tables, and then we can just solve it for y, which is basically simplifying that right-hand side, which is 132 students, which is our y value, which was our number of students, so that matches up with our table of values. Number 3 is if 650 students have purchased tickets, so students would be, if we looked at our xy table, 650 students was our y value. We're trying to find what the x value is. So we're going to go back to our equation that relates the two variables, and 650 is going to get substituted in for y because y was the number of students, and then we have 6x. And what we're going to do from there is just solve for x, which requires us to do a step to divide by 6, and we get x is equal to 108.3 tables. Now, we can't have a partial table, but we have to think about this in the context. 108 tables will not sit all the students. There's that still 0.3 that's remaining. So we need to actually round this up and have 109 tables in order for us to accommodate the 650 students. And that's actually our answer to this question is 109 tables. Again, 108 will not be enough tables. We need 109. Question 4, can we have an input of 4.5? That's the number of tables. So can we have 4.5 tables? We cannot just fold out like half of a table. So we actually need whole number values here. We need 4 tables or 5 tables. And so the answer would be no, because we need whole number of tables. We cannot have half tables. And is there a representation that best represents the situation? This is going to depend on what you see and what you visualize, with the understanding and knowledge that each of these representations represents the scenario. It just shows it in a different way. So I want you to fill that out on your own, just based on what you know and what you've seen about the one representation that's better for you visually. Thanks for joining in on this. Again, these representations all show the same situation. They just model it in different ways. And we want to be able to connect all of the different representations together.